Find the peak flow rate, Q sub P, in cubic feet per second. In this problem, three watersheds, A, B, and C, are adjacent to each other and measure 120 acres, 160 acres, and 220 acres in size. The runoff coefficients and time of concentrations for each watershed are provided. All three watersheds discharge to a common point, and the intensity equation for the region is given. Since the problem states to use multiple triangle hydrographs with a time step of 5 minutes, our strategy will be to determine the individual hydrographs for each watershed and then add their values together to calculate a hydrograph for all three watersheds combined. The two characteristics which define a synthetic triangular hydrograph are the peak flow rate, Q sub P, and the time to peak, T sub P. These two values define one of 3 points of the triangle. A second point is at the origin of the hydrograph, where time equals 0 and flow equals 0. And the third point is located at flow equals 0, time equals 2.67 times the time to peak. Oftentimes, these two red lines are called the rising limb and the receding limb. Unless a time to peak is provided, it can be approximated as 0.67 times the time of concentration. The times of concentration are plugged into the equation, and the times to peak for each watershed are calculated and rounded to the nearest minute. The peak flow rate, Q sub P, is calculated using the rational method, where the peak flow rate in cubic feet per second equals the product of the runoff coefficient, C, the intensity, I, in inches per hour, and the area, A, in acres. The problem statement provides the runoff coefficient and the area. To find the intensity, we'll use the given intensity duration frequency curve, which relates the time of concentration to intensity for a given return period and location. Plugging in the time of concentration, T sub C, for each watershed, the intensities calculate to be 4.72 inches per hour, 4.02 inches per hour, and 3.09 inches per hour, respectively. Returning to Q equals CIA, the runoff coefficients, intensities, and areas are plugged into the equation, and the resulting flow rates equal 385, 534, and 537 cubic feet per second for basins A, B, and C, respectively. Lastly, we'll want to calculate the total duration of the hydrograph, 2.67 times the time to peak. Oftentimes, this value is assigned the variable T sub B for time of base. Keeping our peak flow rate, time to peak, and time to base values for the watersheds, the triangular hydrographs can be plotted. Watershed A will be in blue, watershed B in orange, and watershed C in green. Since the problem states to use a time step of 5 minutes, we'll need to interpolate to find the flow rate every 5 minutes. Using watershed A as an example, the peak flow rate is 385 cubic feet per second at 15 minutes. And the beginning and ending flow rates are 0 cubic feet per second. The remaining flow rates can be calculated by interpolation. This process is repeated for watersheds B and C, and the flow rates for each time period for all hydrographs are added together. For example, at 5 minutes, watershed A generates 128 cubic feet per second. watershed B generates 134 cubic feet per second, and watershed C generates 90 cubic feet per second. These values sum to 352 cubic feet per second. This summation process repeats for all time periods, 10 minutes, 15 minutes, and so on, until there is no more flow. If we rescale the flow axis, the peak flow rate equals 1200 cubic feet per second at a time of 20 minutes. When reviewing the possible solutions, the answer is B.